Welcome back to our course on compiler construction. In today's lecture, we're going to take a closer look at scanner generators. So first, we're going to take a look at DFAs, deterministic finite automata, and how they relate to another way to express them, so-called regular expressions. We'll take another look at an alternative form of automata, the so-called non-deterministic finite automata, or NFAs, and we'll show a way how to transform regular expressions to NFAs and the other way around. So, in the previous lecture, we've already seen this DFA, which recognizes floating point numbers. So we start with an initial state as 1 here, indicated by the incoming arrow, which has no predecessor. Then we'll recognize one of the digits 0 to 9, and optionally more of those. S2 can already be an accepting state here, and optionally we can go from S2 if we see a decimal point or a dot here to another state S3, which accepts an arbitrary number of digits again. So here we can have decimal numbers consisting of at least one digit in front of the decimal point, and then optionally more digits in front of a decimal point, or no decimal point at all, or a number of digits before a decimal point, and 0 or more digits after the decimal point. So this DFA was able to tell you whether a character sequence that we input is a valid decimal number, so integer and optional fractional part, or not. And we just start with an initial state and then follow the edges, consume one of the input characters whenever we follow one of the edges, and then we have deterministic choices here. So if there's a digit as the input here, we go using these transitions, and if there's a dot as the input, we use this transition to move along our DFA. To talk about DFAs, we've introduced lexemes. So lexemes are the units of lexical analysis, or in terms of grammar for human languages, it would be words, and you can compare them to something like dictionary entries. And in lexemes, we can have common patterns which we want to express in terms of our DFA. So we want to build simple partial DFAs to recognize some of our common patterns that show up in lexemes. So the first common pattern showing up in lexemes is just a sequence of specific parts or characters, which means we just start with a state, then read the first character of that sequence, for example an A here, go to the next state, and then we accept the next character like a B here. So this simple partial automaton here detects a character sequence A, B. In other patterns, we might want to be able to recognize repetitions, for example repetitions of the digits in our floating point number. So repetitions can be expressed by using loops in our graph. So for example, this partial DFA here is a DFA that recognizes any number of queues in a sequence. So you can choose never to go along that edge here, so you'd recognize 0 queues, and you can recognize multiple queues by going along that edge multiple times here. And the third common pattern is to choose between alternatives. So choosing between alternatives means you have a single initial state, and from this state you have 2 or more outgoing edges, which indicate the different choices you can make. So if you want to recognize either an A or a B, you start with a state here, and then you have one edge accepting an A, going to a different state, and you have a different edge accepting a B, going to that state below here. Now, to make work and life easier when using DFAs, you can use something like a formal notation, which we've already seen shortly before. So because drawing graphs is quite tedious, time consuming, and it's difficult for a computer to understand a graph form, for example, drawn on a computer or on paper, we can express our DFA in a more formal way. So a DFA is a 5-tuple consisting of elements Q, which is the finite set of states, so whatever is shown in our circles here. We have an element sigma. A sigma is a different finite set called the alphabet, so the characters you are going to recognize as part of your scanner. So for example, digits from 0 to 9 and the decimal point. Then you have this delta, which is a function. And this function takes the current state you're in, like S2, and an input character, for example, S7. And it gives you another new state. So if you're in S2 and you read a character 7, you end up in S2 again. That would be one part of your delta function. Additionally, you need to indicate in which state your automaton starts. So you have a single state. This is not a set. Q0, which is part of our states, which is a start state. This is S1 in our case. And finally, you have a subset of all the states F, which is the set of finite or accepting states. And here S2 and S3 are the accepting states indicated by a double line around the circle. And you've also seen that we can have a different notation for our delta function. We can express it as a table. So our simple DFA here could be formally noted like on the right hand side. So the sets of states is S1, S2, S3. The set of input characters or the alphabet is just all our digits and the decimal point. So 0, 1, 2, 3 and the decimal point at the end. We start our automaton at state S1. Our automaton is allowed to finish in states S2 or S3. And our delta function is now expressed at this table here, which is a very convenient way, as we've seen already, to store it for a computer. And we've also seen that we've introduced these red error states here, which is not indicated here directly in the graph, where we could just move to an error output because the input would be invalid. So let's take a closer look at the various parts of the DFA. One of the important parts is the alphabet. So an alphabet is a finite set of symbols, so you cannot have infinite alphabets. And symbols are usually represented as characters, for example, ASCII characters. So very simple examples are 0 and 1 as characters. This is the alphabet of binary strings with which you can build, well, just any binary number you like of any length. You can have something else like uppercase A to Z, lowercase a to z, and digits 0 to 9 would be the alphabet of alphanumeric strings. For example, that might be a valid notation for variable names in some programming languages. So this is the alphabet, and from an alphabet you can build a language. So a language is a set of valid strings. A string is just a sequence of symbols which you can build from that alphabet. So for example, you can have a language which consists of the sequences 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0. And this is the language which we would, in natural language, describe as even positive binary numbers which have a value of less than 8. And we've already seen that a finite automaton accepts a language. So if a finite automaton accepts a language, so we read a character sequence, we arrive at a accepting state, and there's no more characters coming, or if there's more characters coming, we ensure that when the last character was read, we have arrived at an accepting state. Then we have successfully recognized a word from the language our automaton is supposed to recognize, and if not, we have found an error in the input. So an automaton decides whether or not a given string belongs to the language described by it. So if we have multiple languages defined, we can define operations on these languages. So we can define the union of two languages using the union set symbol here. So a word S is part of the union of language 1 and language 2 if S is in L1 or S is in L2. Please note this is not an exclusive OR, so it can even be in both of them at the same time. In addition, we can have concatenations of languages. So just written L1, L2, which is defined as the set of sequences S1, S2, so of words S1, S2, where S1 is always part of the first language and S2 is always part of the second language. So we just write two words one after the other, and if the first word is part of L1 and the second word is part of L2, it's also part of L1, L2 of this concatenation. We can also have a concatenation of a language with itself. This is simply called multiplication, or to be more precise, a Cartesian product. So for example, LLL is just a set of words which contains 3 single words, and each of these words has to be part of our language L. And finally, we can have so-called closures. So a closure L star is the union of 0 to more languages Li. So this is a so-called clean closure. So we have 0 or more strings from L if we write L star. And we can also have L plus, which means it's the union of at least one or more elements of Li. So this is a so-called positive closure, which means we need to have at least one string from L as part of L plus. Now this is a bit formal, so let's give some examples for the various operations here. First, for the union of languages, we have two languages L1 and L2 defined here. So L1 consists of the words 000, 010, 100, and 110. We've already seen this language. These are the even numbers in binary that are less than 8. And we have another language, 001, 011, 101, and triple ones. And as you can easily figure out, I think these are the odd numbers written as binary that are less than 8. So if we take a union of these languages, L1 unified with L2, we just add these two sets together here. So if there were duplicate elements, as always in set unification, they would only show up once. Here we have separate elements which do not overlap. So we just write all of the elements inside of our new set, L1 unified with L2, which implies that we have all the numbers, even and odd, written in binary, which have a value of less than 8 in our final unified set here of L1 and L2. Now let's look at concatenation. So let's say we have two languages, and here we express the languages again as a set of strings that belong to the language. So we have language 1, which is expressed as either the string AB or the string C. And we have another language L2, which is expressed as just one word which has the value X. So if we concatenate L1 and L2, we just build a combination of all elements of L1 with all elements of L2. Now that's pretty easy because we only have one element in L2. So essentially we combine the first element of L1, AB here, with the only element of L2 and end up with a new string ABX. And then we combine the second element of L1, which is our C, with the only element in L2 and obtain CX as the result. If we do a concatenation of a language with itself, so this so-called multiplication, we end up with something like this. Let's say we have a language just consisting of these two words A and B. And then if we concatenate that language twice with itself, so we have LLL, then we have a combination of, well, all the letters in L repeated 3 times in any combination. So we start up with A and have another A and another A, and then we have A, A, B. So we take the second one here, ABA, ABB, and so on. So all the possible combinations here until we end up at triple B. So finally we can have a look at our closures. So L star, the clean closure, means we have 0 or more strings from L. So for example, if we have a language A, B, and C as before. So only these two words. And we take the clean closure indicated by this little star on top here. We end up with, well, A, B, as we've seen. So just one string from L, or the other single string from our language, which would be C. Or we can have two strings from L concatenated after another, so AB and another AB. Or we can concatenate A, B, and C. And we can go on and on. So we can, for example, concatenate C with AB and another C, or C and AB, and so on and so forth. Now, we've seen this is 0 or more strings. So this is a new sort of language, which actually has an infinite set of members, even though we started with a finite description of the language using the clean star. And there's one special thing you might have noticed already. This is this little epsilon here in front. So we've seen a clean closure allows 0 or more strings from a language. So how do we write 0 strings from a language? Sometimes it's just written using two of these double quote symbols here, with nothing in between, but that's very confusing. So what we want is something to indicate that we have an empty string, so 0 characters in this string, and that's the epsilon, which is also commonly used as a symbol for the empty set in mathematics, which is quite a good equivalence here. So always when you see an epsilon, it indicates that it's just the empty word. It's not part of our alphabet here. Now if we turn to L+, so the positive closure, this means we have one or more strings from L in our language that we compose by using this closure. And this means we start with this language here, for example, A, B, C. So 3 words in our language, A, B, and C. Then we can take just a single word from the language. So we have an A and a B and a C in our language. We can take 2 of them. So we have AA, AB, AC, and all the other combinations. And then we start with 3 of them, AAA, AAB, and so on until we run out of time or memory, obviously. So again, we see that we can describe an infinite language using a finite construction here. And of course, we have a simple equivalence. So if we have L plus and we add just the epsilon as a set element here, so we combine the set consisting just of the empty word and the set generated by L plus, we end up defining our clean closure L star. Now, writing languages like this works pretty well and it helps for formal proofs, but if you want to use it in practice, there should be an easier way to describe languages, which is more useful for humans to be able to describe these. And you've probably seen very similar parts when you use the command line in Unix or MS-DOS Windows so far, because there you have several different ways to abbreviate names for example, files or directories. For example, if you type dir or ls a star, you get a listing of all the file names starting with an A and then having an arbitrary number of characters behind this. Now, regular expressions are similar, but they use a different syntax. So what you see in the typical Unix shell or DOS Windows command prompt is a very simplified form of regular expressions, which unfortunately uses a different syntax. So let's start defining regular expressions here. So we'll start off with an empty string, epsilon, and some alphabet sigma, which we're going to operate on. And now we can recursively define regular expressions. So we'll start with very simple cases, our basis for our recursion. The empty string epsilon is already a regular expression, and we can build a language out of this, and L of epsilon, the language just defined by epsilon, is the language which has only epsilon in it, so the empty word. Of course, this is not very useful in itself, but it's a useful building block. The second basic element here is if a character A is part of our alphabet sigma, then this character A itself is also already a regular expression, and L of A, the language generated by this symbol, is the language that only has the symbol, the character A in it. And from this basic, introduction here, we can induce several more complex elements. So again, we're going from very simple cases to constructing more complex cases here. So we have the first induction here. If some regular expressions R1 and R2 are regular expressions, then we can write R1 or R2 as the regular expression for the unification of the regular languages generated by R1 and R2. This is a so-called selection operation. Again, if both R1 and R2 are regular expressions, then R1, R2, just written one after the other, is the regular expression for L of R1, L of R2, so our concatenation operation. The third induction rule is if R is a regular expression, then R star denotes L of R star, so the clean closure of the language generated by our regular expression R. And finally, we have something we haven't seen before. So if we put our regular expression R in brackets, it's just a regular expression denoting the language generated by this regular expression R. So essentially, we can add parentheses to group parts of the regular expressions to make them easier to read and write. So this is very formal. So let's take a look at some examples how these regular expressions relate to our automata. Let's take a closer look again at the DFA, which accepts decimal numbers. So we start with an initial state as 1, and then we read a character which has to be one of the digits 0 to 9. So this is equivalent to just writing a simple partial regular expression which just says I want to accept any of the characters 0 to 9, which we write in a shorthand form with the square brackets here, and then the first character in this sequence, then the dash, and the last character in this sequence. Of course, this implies, like we've seen in the ASCII encoding in the previous lecture, that the digits 0 to 9 come one after the other in our encoding. So when our regular expression has determined, okay, the first character we read is somewhere in between 0 and 9 inclusive, we can go on to the next one. And here we have a choice. So in S2, we can either say, okay, we're finished, that's it, nothing more is coming, or we can read another arbitrarily long sequence of 0s to 9s, or the third option is we can read the decimal point here. So what we can do is we can read another arbitrary sequence, so clean star, 0 to multiple iterations of digits, or we can just stop here. We'll see how this works in a bit. Or we can read something which comes after this, and this is always started by the decimal point. So we can go this direction here, read a decimal point, and after we read a decimal point, we can read 0 to arbitrary many items of a digit 0 to 9. And to indicate that this part here is completely optional because S2 was already an accepting state, we put brackets around this second part here, just to indicate that all these belong together. And then we add a question mark. So this question mark indicates this is optional. So there's either one instance of this whole partial regular expression here, or 0, which means we would stop here and we would just read at least one digit. So again, this abbreviated notation used for regular expressions looks like this. We can read any character, which is dot. Now this is confusing, right? Because here we read a actual character, which is a dot in quotes. So here you must be careful to differentiate. And this is a common problem when reading and writing regular expressions. Is it actually a character of your input character sequence, or is it a character which has special meanings for constructing regular expressions? So you've seen here the square brackets are special because they indicate a range, like here. And you can also just write A, B, C if you have single instances of characters inside square brackets. The star has a special meaning because it indicates our clean closure. The question mark and the round brackets have special meanings. And this dot here, you must be very careful with when writing regular expressions, because if you write it like this, so you see this is an error in our slide actually, it would mean an arbitrary character. If you wanted to read a dot ASCII character here, you would usually, and this depends unfortunately on the style of regular expressions you're using, either write it with single quotes around it or write a backslash in front of it, whatever. So here you have an example of having to be a bit careful about this. And this is very common when writing regular expressions, that you get something like this wrong and then it starts accepting something you don't expect or refuses to accept something you think it should actually accept. So we've seen we have 3 ways to describe a language now. So the first one is using these graphs for DFAs we've seen before. So these graphs provide a very quick overview of the structure of a language. To make it easier for computers, you can use tables for our delta function. So these tables help to write programs and make it easy to change them to implement your DFA. And you can use regular expressions, and these can help generating the accepting automata for a language automatically without having to write the tables manually. All of these 3 representations are equivalent. We have not shown, and we are not going to show, a formal way, or not going to prove it at least, to transform one representation into the other, but maybe it's still possible for us to see it. So the so-called family of languages that can be recognized by automata or regular expressions is called the regular languages. And these regular languages are an important and powerful class of languages, but they do not cover all use cases. For example, which is very important because beginners with regular expressions sometimes get this wrong, recursion in a language cannot be specified using regular expressions. So regular expressions are unable to count. But we'll see more of this later on in the term of this course. So how can we construct automata to recognize more complex languages? Let's look at a simple example. Let's say we want to construct a language that includes the 2 words all and So we can build very simple DFAs to detect each of these words separately. So we start here, then we detect an A, then we detect an L, then we detect another L, and then we're in accepting state. So the first automaton here detects the sequence all, and the second one is A, N, and D. So this detects our word and. Please note that we left out the numbering of the states here because it's not important in this example. So it just makes things easier to read. Now, the previous slide showed how to detect these words separately. Now what we want is a language to include both words. So we need to build a combined automaton that can recognize either the word all or the word and. So how can we do this? Let's try to combine both DFAs. How can we do this? Well, let's join the starting and the accepting state of both. So we start here, we read an A, L, L, we end up in the accepting state, or we start here, we read an A, N, D, and end up in an accepting state. Wait, I think you see there might be a problem. So if we start here and read our first A, our automaton needs to decide if it has to go up here or go down here. But since we only read a single character at a time, so if we read this A, we don't know if there's an L or an N following, our automaton doesn't know which way to go. So walking the DFA, as we've done before, does not work anymore. If we read an A, we need to choose between one of the 2 alternatives. And now let's say we have and at the input, but our automaton chose to go the upper way here. So it read the first A, went to S1, and then the only way to go forward here is to read an L. But we have an N at the input because we had an input word of and. So our automaton is stuck because it's unable to go back. We would need some way to backtrack here. And this is very, very complicated and in the common case even impossible to build. So we need a more advanced way to do this. So an obvious solution here is to combine the states S1 and S2. So essentially we can postpone the decision which path to choose. So we can start here, we read an A in any case, and then we split only at the second state. So now if we read an L, we go up here, read the second L, have detected an all, or we can read an A, read an N, and a D, and we have detected AND. So walking the DFA works again, but we need to determine now, in building the DFA, which parts of both words actually are common. And the interesting question here is, can we actually generalize this approach? Now, another way to do this is to introduce a new class of automata. And these are the so-called non-deterministic finite automata. So in deterministic finite automata, you had to choose a way, and you always knew which way to go if a certain input character was there. So you could not go an arbitrary way because you had two choices of going inside your graph when an A was detected. Now with an NFA or non-deterministic automaton, you can admit multiple transitions from one state on the same character. Alternatively, you could allow transitions on an empty input epsilon, so without reading a character. So that's something new. So we could build this automaton if we just gave up on our requirement to be deterministic. So this automaton would somehow magically know which way to choose. So either it would go here or it would go there. Or you could also accept it as it would take all the passes at the same time, and the one where it actually finished in an accepting state, well, you lucked out because that's the accepting one. And both notations are equivalent, so you could either have this choice between A and A in the first state, or you could say you can just go arbitrarily to that one and that one here, and then have the single recognizers for all and AND that we constructed in the beginning, recognizing stuff, and then without reading a character, you go to the accepting state. NFAs can be very easily constructed from regular expressions. So for example, the regular expression to describe our language would just be all or AND, and the equivalent deterministic variant would be A followed by either LL or ND. So we see the two subautomata we started our description with can be easily identified in the graph. So the first subautomaton is shown in this pink color shade here. So the first subautomaton, or just machine 1, recognizes all. And the second one, here shown in this ochre color, is the automaton to recognize AND. And then we can just combine them by adding a joint starting state, passing to both automatons using an epsilon, so an empty transition here, and then at the end of both subautomatons you use an empty transition again to go to your final accepting state. So if we want to construct a scanner, let's take another look at the parts of our regular expression. So first we have a single character which stands for itself with our special case epsilon, the empty character. Then we can have concatenations, so R1, R2, writing two things after another. We can have selections, so either R1 or R2. We can have just a grouping here, R1 with round brackets, and we can have our clean closure, R1 star. And we've seen we can construct an NFA for each of these as long as the parts themselves, R1 and R2, are themselves valid regular expressions. So here we have sort of a recursive definition. It's important to know that each DFA is also a valid NFA that simply has 0 epsilon transitions. So we know if we have a deterministic automaton, of course, this is also non-deterministic, but we have only one way to walk through it. Formally, we can say the set of DFAs is actually a subset of the set of NFAs. So let's start out with characters. Single characters and epsilons in a regular expression just become transitions between two states in an NFA. So we've seen, for example, all and AND. The transitions are, well, we have an A, we have an L, and we have an L. So these are the very simple transitions, just recognizing successfully a single character. And for the AND, we have an A here. Again, we have an N, and we have a D. Now we can combine these simple regular expressions by putting these characters one after the other. So we have concatenation here, we have regular expression 1, regular expression 2, and if we want to join them and recognize a sequence of R1, R2, we just join the overlapping state here, so the accepting state of R1 becomes the initial state of R2. So in our example, we just write A, L, L, as we've seen before, and accept it, and we can write A and D and accept it again. The selection operation works similar, so we introduce a new start and accept states and attach them using epsilon transitions. So we have two regular expressions, R1 and R2 again, and then we join them up by building an alternative selection. So we start up here with an epsilon transition, up here, down here, and we join again to a new accepting state, again using epsilon transitions. So in our example, we have R1 recognizing all and R2 recognizing and. So we build a new start state using the epsilons here. We build a new end state using the epsilons, and we have a new regular expression that recognizes either the word all or the word and. Finally, we can do grouping. So these parentheses just delimit which parts of an expression to treat as a subautomaton, so they make stuff easier to read. And they are just they're part of the structure, but they're not nodes or edges in the graph. So they just describe grouping in our graph or structure of our graph, but they're not elements describing any transitions in our graph. So the automaton for all and could also be written as A in brackets, L in brackets, L in brackets, or A in brackets, N in brackets, D in brackets. Of course, you don't do it as long as it's obvious what you mean, because this is just nasty to write. So finally, we're left with our clean closure. So R10 means 0 or more concatenations of a regular expression R1. To do this, we introduce a new start and a new accept state and add epsilon transitions to it. So we can either accept a single walk through our regular expression R1, or we can loop back to the start of R1 to allow any number of repetitions, or we can bypass R1 entirely, so we have 0 walkthroughs. So we start with our regular expression R1 here, which you can see again here. So we can have either 0 repetitions of it, so we built an epsilon transition which straightly goes to the accepting state without reading any characters, which is fine because that would be just an empty input. Or we can go using an epsilon transition to the start of our regular expression, go through it once, and end up at the accepting state. Or we have this repeating epsilon transition here, which means we start with one instance of R1, go back to the beginning, read the next instance of R1, and so on until we end up at an accepting state. So what have we achieved so far? So we didn't have a formal proof, but we have shown by construction that we can construct an NFA for any given regular expression, independent of whatever the contents of that expression might be. And this is known for quite some time. This is called the McNaughton-Thompson-Yamada algorithm, and here are 2 literature references for the original papers if you want to dig deeper into this. Now, how about the positive closure R1+? So we've talked about this, but we haven't built this so far. So R1+, as we have already seen, can be made from the concatenation and clean closure. So we write R1 once in any case, so we have one repetition of R1 independent of what else comes behind it, and then we just use R1 star as the clean closure, and you can try it yourself to see that it works. This is handy to have as notation, but it's not necessary to prove that our construction works. So to finish this lecture, some wise words and references. So Jamie Tuszynski, who was an early engineer on the Netscape web browser project, wrote more than 20 years ago, some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have 2 problems. So regular expressions need some practice to use them efficiently and successfully. So when you use them, especially if you're going to use Unix later on in your career, it's very useful to have a basic solid knowledge of regular expressions. You can use them on the shell. You can use them in tools like set or awk to work on character sequences to filter text. You can use them in scripting languages like Python. So they're very useful if you do any sort of text processing. And here on the bottom are two literature references to the papers introducing this construction and the equivalence of regular expressions and automata. And you see these are quite old already, so from 1960 and somewhere in the late 1960s. And of course, you might recognize the name of Ken Thompson as one of the guys involved in early Unix and C developments. And I think he's still involved in defining the Go language at Google nowadays. So that's all about regular expressions and automata for today. Thanks for listening, and until next time.